Most people who are interested in research just want to know. They just want to know, why does it work this way? How does it work? Could we make it work differently? If you were designing the universe all over again, what would you do differently? You need people like that, because otherwise, how would you ever learn anything new? I actually did not start out thinking I was going to be a computer scientist or anything like that. I knew I was going to be some kind of a scientist. By the time I was 10, I was playing with chemistry sets and reading books like The Boy Scientist. Eventually, I did my undergraduate work at Stanford in mathematics, but I took all the computer programs I could. And then I went to work for IBM for a couple of years. And after 2 years at IBM as a systems engineer, I realized that I needed to go back to school and understand more deeply how operating systems worked and how compilers worked and things like that, algorithms. So I got introduced to a man named Gerald Estrin by my best friend, Steve Crocker, with whom I'd gone to high school. And Estrin became my thesis advisor at UCLA. And I was pursuing a computer science degree, PhD. And in the middle of all that, the ARPANET project got started, and Leonard Kleinrock, who was one of Gerald Estrin's colleagues in the computer science department, asked me and Steve Crocker and John Postel to work with him in the Network Measurement Center. So I got sucked into the ARPANET project, and that's a permanent infection. Once you are infected with networking, you never get rid of it. And so, maybe 50 years later, here I am, still running around spreading the networking disease wherever I can. Mathematics has this wonderful character to it that if you can figure out the answer, there it is. I mean, that's it. There's the answer. The equation gets all sorted out. Unlike physics, where physics has to confront the real world, things don't always work the way you expect them to. And in the world of networking, there's something else that's very satisfying. It's a little bit like programming. Programming was attractive to me because you could create this little universe and it did what you told it to do. Of course, that was the problem. It did what you told it to do, not what you wanted it to do. And the difference between what you wanted it to do and what you told it to do is called a bug. And I learned very quickly it was easy to create bugs and it was hard to find them. But the idea of being able to create your own little world and make it do things is really mesmerizing. And networking is a lot like that. It's being able to create this infrastructure that allows things to communicate that never talked to each other before, no matter where they are, no matter how far apart they are. So there was something magic about doing something in Los Angeles that caused something to happen in Boston or New York. Well, you know that we have been sending spacecraft out to explore the solar system for many years now. And importantly, in 1997, we delivered a small rover called the Sojourner in the Pathfinder project to Mars successfully in 1997. But someone noticed that they had sent orbiters to Mars in order to map the surface of the planet to decide where the rovers were going to go. And so the team at JPL decided to reprogram the rover and the orbiters so that we could send data from the rover up to the orbiter when it got to the right place in its orbit, and then the orbiter hung on to the data until it got to the right place in its orbit to transmit data back to the deep space. Now, why was this a good idea? We got 128 kilobits a second up to the orbiter and another 128 kilobits a second back to Earth. So store and forward turns out to work better. Oh, by the way, that's how the ARPANET works. Oh, that's how the internet works. It's store and forward packet switching. And so we're all pretty excited that that technology is the future for interplanetary communication. So let's go back to the 1950s. It's after World War II. Computers during that period of time had been used for military purposes, ballistics calculations, and of course code cracking at Bletchley Park in the UK. But the computing capability became obvious that it was flexible. You could do anything that you needed to calculate if you could figure out how to write the program. So some people recognized there were business opportunities to do business data processing. So the 1950s is a blossoming of computing. And now the question is, at this point, computers are still very expensive. We're talking millions of dollars of $1950, which is really expensive. But as time has gone on during that period, in the next 10 years, the cost of the machines comes down. We can start applying them in ways that we wouldn't do previously because it was too expensive. And at this point, we're starting to see in the mid-1960s the possibility of using computers in communication to manage computer-to-computer communication. Computing became a focus of attention at the Information Processing Techniques Office of ARPA in the mid-1960s. And they now realize at some point that every year, each of the computer science departments says, you have to buy us a new world-class computer so we can keep doing world-class research. And even ARPA couldn't afford to do that. And so they said, you know what, we're going to build a network, and we're going to connect all of your computers to each other. So you can share your computing power, you can share the results of your research, you can share each other's software, so we can accelerate the rate at which artificial intelligence and computer science develops. And that's where the ARPANET came from. It was to connect these computer science departments together. And ARPA was very smart because they said, you know what, we are going to fund all of you. So instead of hiding your result in order to have an edge in a competitive bidding process, they said, we're funding all of you, share your results. So the ARPANET gets built and it works. And so now we have a worked example of a computer communication system that allows disparate machines from different manufacturers, such as IBM and Univac and Digital Equipment Corporation and Xerox Data Systems. All these machines are now interacting with each other thanks to the leadership of a guy named Steve Crocker, who essentially led the network working group to develop the protocols that were needed to make those computers talk to each other. So Steve Crocker and I meet in 1959 at Van Nuys High School. We immediately realize there's no math club, so we start one there. We actually don't know John Postel yet. We don't see and meet him literally until we all three of us get together at UCLA some years later. But at Van Nuys High, Steve and I were very active in the math program. And then we all went off in our different ways. I went to Stanford, he went to MIT, and John ended up at UCLA. Later, Steve comes to UCLA for his graduate work, and I'm at work at IBM. This is in the mid-1960s, and John, I guess, is there as well at UCLA. And in 1967, I decided it's time to go back to school to get an advanced degree, and that's when Steve introduces me to Jerry Estrin. So the three of us, Steve and John and I, are at UCLA as graduate students, and about that time, the ARPANET project gets started. So the three of us end up working in that laboratory, and as they say, the rest is history. So Bob Kahn was at Bolt, Beier, and Newman. Actually, he started at MIT. And while he's there, he gets some advice that he should go and get some experience in the real world. And so he ends up at Bolt, Beier, and Newman. It's intended to be a short-term arrangement. And while he's there, this ARPANET project blossoms. And Bob and his colleagues write the winning proposal. So Bob is there as sort of a system architect. The ARPANET project is going to be built at Bolt, Beier, and Newman starting in early 1969. And they deliver the first node of the ARPANET to UCLA. So Bob comes out to UCLA in early 1970, it's probably January, along with his colleague Dave Walden, and they want to kick the tires of the four-node network. And so my job is to write software that will drive traffic into the network. And what Bob wants to have happen is he wants to kill the net. He's saying, you know what? There are situations under which this thing is going to congest or it's going to get jammed up. Nobody believes him. So he and I get together in the early 1970s, and we proceed to kill the network repeatedly in a variety of different ways. So Bob goes back happy. telling his colleagues, see, we need to fix the protocols to keep it from breaking. And I come away realizing that I've just had one of the best experiences in my life working with somebody who's as creative as Bob is. That's the beginning of a 50-year friendship. Starting in 1973, Bob Kahn is now gone from Bolt, Beranek, and Newman to ARPA in late 1972. And I have gone from UCLA up to Stanford University to join the faculty. So in early 73, Bob shows up in my office and says, we have a problem. And my reaction is, what do you mean, we? And he says, well, here's the situation. ARPA has decided that computers are going to be useful in command and control. We know that we're going to need voice, video, and data. We know that the computers are going to have to be in mobile vehicles, they'll have to be in ships at sea, and they'll have to be in aircraft. But the ARPANET that we just finished building was connected together by dedicated telephone circuits connecting the packet switches to each other. You can't use dedicated telephone circuits to connect the car to the network. You need radio, and you need satellite for the ships at sea. So by that time, this is the spring of 1973, he's already working on a mobile packet switch network for radio-based packet switch net and a packet satellite net. So his problem is, how do you hook all those networks together and make it look like one net? So our problem was the internet problem. How do we hook all those different packet switch nets together? What's a protocol that is used to make it look uniform? That's where the internet protocols came from. And that was the origin of the Transmission Control Protocol, or TCP. So we start out, of course, in the spring of 73. He's based in Washington, D.C., and I'm based in the Bay Area, San Francisco Bay Area. So we fly back and forth and have meetings from time to time, every few weeks, often in front of a whiteboard, big arguments, sometimes just pacing the halls and taking long walks. But the problem turns out to be almost solving itself. Here's why. We've got these networks, which we drew as little clouds. That's where this cloud notion comes from. We literally drew these things as clouds because we didn't care what was going on inside the network. It was the edge of the net that was important, because we had to figure out, how do I get from this edge of the net to the edge of the other network? So we said, okay, there's going to have to be a box in between the networks that know how to talk to each network. And there has to be something that lets us refer to other networks besides the one we're on right now. And of course, each of those networks thought they were the only network in the world. They had their own address structure, but it only extended to within that network. So we had to invent an inter-network way of addressing things. So within about 6 months, we figure out how to do this. And we write a paper, which gets published in May of 1974, on the protocol for packet network intercommunication. It's the founding document for the internet. In 1972, ARPA was spending a substantial amount of money at RAND Corporation, along with other places that it was funding to do computer science and artificial intelligence research. And they ran into a budget problem because RAND was a federally funded research and development center. And there were limits to how much money you were allowed to spend on it. So ARPA said to Keith Unkefer, who was running the computer science department at RAND, find another place to operate and take your best people with you. So USC ends up housing the Information Sciences Institute in Marina del Rey. And ARPA, of course, is very happy about that, because now their budget limitation has been removed. They've got some of the best computer scientists in the world at ISI to complement the ones at MIT and Stanford and Carnegie Mellon, University of Utah and Santa Barbara and so on. So the result is this powerful addition to the complement of research teams, all of whom are now being interconnected by the ARPANET, because by that time ARPANET's operational. So the Marina del Rey facility was a particularly beautiful arrangement. It's a big, tall-story building. There were a pair of them adjacent to each other. But it was fortuitous because it had a beautiful view of the harbor. And I remember Keith often arranging the interviews of people he was trying to attract to ISI to be roughly at a time as the sun is going down over the western horizon. And his office had a big picture window, and the person he was interviewing is looking out through the picture window. And Keith is saying, "Wouldn't you like to work at a place like this?" But the real power of ISI was the quality of the people that were there. And Keith he may not have been a technical guy, but he was utterly loyal to ARPA. And if ARPA wanted to get something done, Keith would figure out a way to do that. So let's talk a little bit about John Postel, but I need to take you all the way back to his UCLA days when Steve Crocker and John and I were part of Glenn Kleinrock's operation. The ARPANET project is underway. Steve is responsible for leading the network working group, and he decides we should document what we're doing. And he invents this idea of request for comments, or RFCs. And then he decides he's going to go to ARPA. And so he turns to John Postel and he says, "John, why don't you be the editor of the RFC series?" And John accepts that. And in the early 1970s, as the Internet project takes off, he becomes the Internet Assigned Numbers Authority, or IANA, to handle all of the registration of IP addresses, the assignment of domain names, which is an invention that comes along with the Internet, and the parameters of the Internet protocols. John is a master of all of these functions that are so core to the Internet's early story. He was also cantankerous when it came to editing documents. I mean, he demanded that we write well and spell things correctly and be technically correct. This, by the way, is really important because he could have been just a text editor and gotten the English right, but he actually understood the technology, and so he demanded high-quality documents that were going to be useful for people who were trying to implement the protocols that were described. And so John was sort of the perfect match for this particular task, and he did this for literally the rest of his life until he passed away in 1998. When I joined ARPA, I started wearing three-piece suits. This is because my wife was from Kansas, and when we moved from Stanford to Washington, D.C., she said, "Washington, D.C., three-piece suits." The only reason I bring this up is I want you to imagine John Postel with his long beard, sandals, and hippie style, and me. It looks like the Pope meets the heretic. That's basically what that picture would look like. Crocker is a truly modest person. The most unauthoritative thing he could call this series of documents was request for comments. Please help us figure out whether we're going the right direction or not. It's classic Crocker. And he thought hard about that. He really worked at that. So that's where that term comes from. In terms of naming things, originally we were not very creative. I mean, the host names of the ARPANET were UCLA, MIT, BBN, CMU. I mean, really exciting. And then, of course, if there were more than one machine at those locations, those names might be IBM.UCLA. It did happen in the earliest stages of the ARPANET that we just had a list of all the names of the computers plus their digital addresses in the ARPANET. And there was a document that was sent around that was updated every day or two or maybe every week that gave everybody the list of the host names and the addresses that they belonged to. And we adopted that policy when we started building the Internet. We had the same, this document that went around. But that wasn't sustainable. It wasn't scalable. And so it became very clear that we needed to do something that was much more automatic and that allowed people to remember just the names and not have to worry about what the addresses were. So a guy named Paul Makapetris, working with John Postel at ISI, invented the domain name system. And that was a core contribution to Internet and its evolution. So the domain name system is what we all think of today. www.google.com is a domain name familiar to some of you. So that was a very important scaling thing. It's a gigantic distributed database, and it has worked extremely well since the mid-1980s. So if we go back to the ARPANET period in the 60s and 70s, it's terminal equipment communicating with hard wires to computers, time-shared computers basically, and then the time-shared computers are communicating with each other through the ARPANET. That same paradigm begins with the internet as well, starting in the late 1970s. But as we start getting to the point where people can buy their own personal machines, whether it's a desktop machine or maybe it's a laptop machine, and of course today we have pads and mobiles, the costs start coming down. People start having their own computers, personal computers, and now those are functioning just like the big host machines do. One of the nice things about the internet design is that it doesn't care whether it's a supercomputer over here and a laptop over there. They're equal from the protocol point of view, they're equal partners. This idea that you have your own computers rapidly gained in popularity, partly because the costs were coming down and partly because of the convenience of being able to do local computing without being connected to anything. What I find interesting is that as we got more and more accustomed to being online, we wanted to be online all the time. We wanted the ability to get access to other resources literally whenever we needed them. And so we went from hardwired things, which only work if you're physically connected somewhere, to radio-based connectivity, whether it was Wi-Fi or packet radio or packet satellite. Now you could be connected all the time. So this thing about being online all the time was a big deal, because it meant, for example, if you were writing an essay and you got to a place where you didn't have an answer or you didn't remember something, you could go and Google it right there on the spot, get the answer, and then keep writing. So we have the kind of civilian use of the computers happening concurrently with whatever thinking is going into how they might be used in command and control. There is attention being paid to speech understanding, to speech synthesis, to image processing, image understanding, and image analysis. And, bits and pieces of artificial intelligence and rule-based systems are beginning to develop. And then around 1991 or so, Tim Berners-Lee at CERN releases what he calls the World Wide Web. The world is ready for a new way of using the internet. It makes the internet more colorful, right? Because it's formatted text and imagery and eventually streaming audio and video. And not too many people actually noticed the 1991 release. 2 years later, in 1993, two guys at the National Center for Supercomputer Applications decide to try to build a graphical user interface for the World Wide Web, and they call it Mosaic. They release that as a free piece of software. It gets downloaded 1 million times in the first 2 weeks. Everybody goes crazy because suddenly the internet looks like a magazine. And now people try to figure out, how can I create web pages to share with other people? And what was astonishing is the avalanche of content that flowed into the internet at that point. Everybody just wanted to share what they knew, and for the satisfaction of knowing it was useful to someone else. Nobody was trying to make any money out of this. There was no pecuniary motivation at all. It was just sharing of information. Of course, now we have a problem, because this massive amount of content has flowed into the internet thanks to the World Wide Web. Nobody can find anything until search engines get invented to go index the World Wide Web. So you get Alta Vista, then you get Yahoo, then you get Google in 1998, you get Bing, and you get a number of other indexing mechanisms. The value of information is not necessarily found by locking it up in somebody's head. It's found by sharing so that other people can make use of that information and apply it in circumstances that you might not have thought of. And so the ability to find information and to share information, to generate information, to use it, and to get help from the computer to use the information is hypergolic. I mean, it is a way of mutually reinforcing the power of computing and the value of information. So it's 1973. Bob and I are working on the internet. Marty Cooper is at Motorola trying to figure out how to build a handheld telephone without any wires. And these two projects, knowing nothing about each other, proceed in parallel until 1983, when we turned the internet on formally, operationally, and Marty demonstrates his handheld telephone. So now we've got mobile telephony and internet, or in 1983, are starting to penetrate, and they are completely independent. They just go their direction independently until the 2007 invention of the iPhone. And suddenly, the internet becomes more accessible because anywhere you can get a mobile signal, you can get to the internet. This handheld thing has got computing capability, a camera, it's got the ability to, it's got a microphone, it's got a speaker. And so suddenly, it becomes more useful because it has access to everything on the internet. And so these two technologies are literally mutually reinforcing. And this is always a happy coincidence when you have technologies that are more powerful together than they are independently. And we see this happening repeatedly in the space I work in, where technologies that used to be independent of each other suddenly come together and have a gigantic impact. So internet has introduced some real challenges for us. First one is just scaling. Just how do I make this thing, serve 7 billion people on the planet, and God knows how many billion physical devices. There are more devices on the internet than there are people at this point. 40 billion, who knows. Second, we find that the internet and the World Wide Web and a lot of the applications are amplifiers. They are powerful amplifiers. And unfortunately, these powerful amplifiers don't know the difference between good quality information and misinformation, disinformation, harmful speech, malware, and all, ransomware, and so on. So we have this amplification problem where we amplify bad stuff and good stuff equally. So we have a really tough problem to try to protect people from harm in this online environment. That's another challenge that's not only technical, but it's also legislative, it's law enforcement, and it's behavior, which raises another interesting problem. Some computer scientists, including me, don't always fully appreciate the consequences of the introduction of technology into a society. Sometimes you can't even predict it. So we now have a challenge to figure out how to cope with some of these emergent behaviors while preserving the value that we can see of the powerful way in which computing and communications and information can work together. Certainly the internet, I've often said, is a mirror of our society. And if you don't like what you see in the mirror, fixing the mirror doesn't do you any good. You got to fix what's reflected in the mirror. That's our society sees what it sees in the internet today and says, we don't like what we're seeing. The response to that is, don't change the internet, fix the society that's reflected in it. And so the question is, how do we create motivations for people to, say, self-censor in a sense? How do we create an environment where people are willing to be thoughtful about what they say and also to be thoughtful about what they hear? So if we were looking for solutions to hate speech and other misinformation and disinformation, the wetware up here could make a big difference. It's called critical thinking. And what's that all about? Well, you should ask questions. Where did this information come from? Is there any corroborating evidence for assertions that are being made? Who put this information up there, and why did they do that? What's their motivation? Are they trying to get me to believe something that I probably shouldn't believe? That takes work, and so not everyone is willing to spend time critically thinking about what they're receiving. If I were to start over again in this whole internet odyssey, I think I would have wanted to have more sociologists, psychologists, neuroscientists, anthropologists, helping us think our way through what the consequences of the technology might be, or at least observing what was happening and to explain in more precise terms what we should do in order to counter the potential negative hazards that are showing up. So artificial intelligence, of course, has been a focus of attention for ARPA from the early 1960s. When J.C.R. Licklider was the first director of IPTO, one of the things that he was interested in was how we could use computers to do non-numerical computation to help people process information better. And so that's been a theme for ARPA from the very beginning. Now, in the 2020s, we are experiencing a renaissance of artificial intelligence because of a particular technology called machine learning. That notion of a neural network that mirrors the way our brains work, as best we understand, was posited in the early 1960s in a single layer system, and it didn't do very much. And in fact, Minsky and Papert wrote a book called Perceptrons, which basically said, this stuff doesn't work. Don't bother. It's a waste of time. Then along comes the introduction of computing capability like graphical processing units, GPUs, which originally were designed to draw little triangles as fast as you could to do video games. But the computing people said, wow, that's really running fast. Why don't we use that to do some other kind of computation? And at some point, the machine learning guys said, we could build a multi-layer neural network model with these kinds of processing units, and they could be hundreds of layers deep as opposed to one. And the depth of the system is what gives it its astonishing capability. What happens is that you expose these multi-layer neural systems to input, whether it's text or imagery or sound or anything else, and you train it to respond. So the multi-layer neural networks suddenly function dramatically well, and they also fail dramatically when they don't work properly. And so they're brittle systems, but they are very deep and narrow. They have led to our ability to understand speech, to generate speech from text, to recognize images. And so we've fallen in love with artificial intelligence now in a way that we couldn't years ago because we didn't have the capability that we have today. Now our big problem is figuring out how to deal with the fact that it doesn't always work as advertised. The classic example was the self-driving car. And if you look at how those work, it is doing image processing and it's recognizing what's going on around it, but there are also some rules that it's following, like don't hit anything. So there have to be some rules that constrain the way in which the artificial intelligence systems actually run. I have to admit to you that I still have a certain degree of skepticism about the philosophical computer, if you like. The idea that we could try to present choices that we consider to be morally justifiable and choices that we consider to be immoral to a machine learning system might be an interesting exercise, but only if the choices are actually presented to the machine learning system in a way that it can understand. So then we have to ask ourselves, under what conditions will the moral choice be presented to the machine learning system in a way that it's been trained to understand? So let's talk a little bit about what the internet has brought us. It has brought us a phenomenal connectivity among people and things, and that's increasing over time. It has enabled the sharing of information at a scale never before possible. It's also allowed people to allow voices to be heard that might never have been heard. And in the early days, I counted that as a very important positive value for the internet. And yet now we're hearing voices that some of us would like never to have heard and wish we could make unheard. And I don't quite know what to do about that, because as a technologist, the problem of misinformation, disinformation, and hate speech and so on is not solvable simply with technology. There's no switch you can flip. Some people will say, well, can't we use artificial intelligence to detect that and filter it out? And the answer is probably not reliably. And there's a whole long story about scientific method. Some people think science is absolute truth, and I can tell you it isn't. What it is current best approximation to our understanding of reality. And when we run tests to check our theories, and the tests don't confirm the theories, no matter how long we've clung to those theories, sometimes a good scientist has to say, my theory is broken, I have to throw it away and start over again based on the results of that experiment. Well, there are arguments that some people may be spending too much time online, and if you look at various and sundry applications where you just get mesmerized, it's like TikTok where you're just zipping through these little 15-second videos, which I don't do, by the way. However, I have to tell you that as a kid, growing up, I had a set of encyclopedias and a dictionary, and it wasn't hard to find yourself spending hours going through, the dictionary, following words to figure out where they came from, or reading in the encyclopedias and then following a thread for hours. So in a very funny way, it's not necessarily the technology that's causing this to happen. It's the people just often are fascinated by information. There's a book called Alone Together, written by Sherry Turkle at MIT. And she spends a fair amount of time talking about kids who are interacting not with each other directly, but through their mobiles. And the point she wants to make is that, which I agree with, is that we should be spending more time talking to each other as opposed to talking to our mobile smartphones. In fact, those kids often are afraid to have phone calls because they have this concern that if you get to a point in the conversation where it's awkward, the silence is very, very difficult to deal with. Whereas texting, you're forgiven if you don't respond because everybody understands that, well, you might be distracted and it's okay. So if somebody asks you an awkward question in a text and you don't respond, it's okay, socially okay. But if you're in a real-time conversation, face-to-face or on the phone, that pause is awkward. And so we see behavior being driven by that, avoidance of the awkward moment. She also does something else in her book, which I find extremely important. She says that when we interact with robots that have humaniform characters to them, they have faces, even if it's a cartoon-like face, that we imbue the robot with social intelligence that it doesn't have. And so then we get insulted and upset if it doesn't seem to be following our lead or empathetic to what it is we're trying to do. It's a very peculiar transference effect. But the bad thing about this is that you make assumptions about the system that you're dealing with that are not merited. And we see this happening in text-based interactions too. In the 1960s, a guy named Joe Weizenbaum wrote a program called ELIZA. ELIZA emulated a Rogerian doctor. And it would say, please tell me all of your problems. And you might say, well, I've been feeling very sad recently. And this program would simply take the input that you typed and transform it into a different shape. So if you said, I've been feeling very sad, it would say, how long have you been feeling very sad? If you had said, I'm feeling very blueberry, it would have said, how long have you been feeling very blueberry? Because it didn't understand what you were saying. It was just doing a transformational grammar. People thought they were talking to a person, even when it went clunk, and they got upset when it didn't seem to respond to them. So we project this social intelligence onto these computer-based systems more than we should. I worry about that. The way I look at this is Bob and I helped figure out a kind of road system and a set of rules for getting the roads to work. So like drive on only one side of the road at a time, not both at the same time. So we had rules of the road, but we didn't say anything about what vehicles to build other than to say don't build them longer than this or wider than this or taller than that or heavier than this. We didn't say anything about the buildings that are at the side of the road. People could build whatever they wanted to. We didn't say what they carried in the cars or the trucks or the vehicles. But we gave a basic mechanism for creating this communications capability and then said, look, this is an open architecture. It's a layered structure of protocols. It's extensible within a layer, and it's extensible in vertically. So, for example, the TCP/IP protocols are two core protocols of the internet. Tim Berners-Lee came along and stuck the hypertext transport protocols on top of that to form the World Wide Web. which was instantaneously global. As I think about what Bob and I did, one of the decisions that we made early on in the Internet's design was that we would give away, without any intellectual property limitations, the design of the Internet. And you might wonder, why did we do such a stupid thing? And the answer is that we realized that when we were designing this for the American Defense Department command and control system, we knew that they would have to talk to allies, and that the allies would need to have a capability that was matching what the Americans had. And so we were thinking, okay, it's 1973, who are our allies? And there was a list. And then we said, but who were our allies 25 years before? And it's a different list. Who will our allies be 25 years from then? And it will be an unknown list. And we said the only way we can be sure that our allies have access to the technology is to give it away to everybody. And so that's what we decided to do. We published it freely. We made no intellectual property claims on it, and I'm glad we did that. Ideas never end. Software is an infinite frontier. You can program anything you can figure out how to program. ISI is a place where imagination reigns. People are free to roam a universe of ideas, to bring some of them to fruition, find out how to make them work, find out how to scale them, find out what's wrong with them. You need people who want to spend time and energy figuring that out.